Myself Dr. W.B. Gandhani from Kamlanil Mahavidyalaya, Nagpur. Today I am going to discuss the third part of carbohydrate. In this, we are going to see some important conversions like conversion of glucose to fructose and conversion of from fructose to glucose, and also we are going to see some conversion, that is aldopentose to aldohexose and aldohexose to aldopentose, and some structure of some important compound like Sucrose, Maltoe, Lactose and Ribose, Deoxyribose and Starch and Cellulose. So the today's topic is third part of the carbohydrate, and here we are going to see some important conversions of the carbohydrates. And here first that we are going to see the conversion of glucose to the fructose, and here this conversion from glucose to fructose consists of some steps are there. So we can say that here this is the conversion from aldose to ketose. So aldose can be converted to ketose, and it contains the total 3 steps, so which are shown in this slide. So first step is glucose is converted to oxygen by reaction with excess of phenyl hydrogen, and in the second step oxygen is converted to ozone by reaction with hydrochloric acid, and in the third step ozone is reduced to ketose by zinc and acetic acid, and aldehyde group is reduced to preference to the keto group. So all these 3 steps are shown here. So in this step, so all these 3 steps are shown here. So this is the first step, that phenyl hydrogen react and get added here in this way. So and we get the oxygen first, and after this oxygen formation, then it is converted to, it react with the HCl, hydrochloric acid, and there is a removal of this one here, this phenyl hydrogen, and we get this ozone. And after this reaction with reduction, and the 2 hydrogen is added here, and we get in the presence of acetic acid and zinc as a reducing agent, and we obtain the fructose. So here this is CO and CH2OH, 2 hydrogen are added. So first conversion from glucose to oxygen, oxygen to ozone, and then finally we get the fructose. So this is simple conversion of glucose to the fructose. And second important conversion is now opposite to that, fructose converted to glucose. And in this case of conversion, again as we know, ketose can be converted to the aldose with the same number of carbon atom by the 4 steps are there. So in the first step, keto group, our fructose is first reduced to alcohol by hydrogen in the presence of nickel as catalyst, and in the second step it is then oxidized to monocarboxylic acid, and in third step monocarboxylic acid is converted to the lactone by heating, and in the fourth step lactone on reduction by sodium amalgam in the slight acidic media give the compound glucose. So 4 steps are there in the conversion from fructose to glucose. So these are the 4 steps shown here. So first here 2 hydrogens are added here, so here becomes CH2OH, here CHOH, 2 hydrogen added, CO becomes CHOH. This is the ketose, or also known as a fructose, because ketose means because CO ketone group is present, and after in the presence of nickel, so we obtain this compound, and after that now here it get oxidized in presence of 2 oxygen, and here this group is converted to carboxylic acid, that is here the COOH group, and now from this H and this OH is reduced, and we get this type of gamma lactone, and here 4 carbon and this attached here with the oxygen, and water is replaced minus H2O, and then again reduction by using sodium amalgam and in presence of acid. So 2 hydrogens are added here, CHO, and it becomes CHOH, and here also CHOH. So we get aldose or glucose. So carbon number of carbons are same, and fructose can be converted to glucose. So this is the second important conversion from fructose to the glucose. And another 2 important conversions are also there, that is we have seen here that same number of carbon atom, but now important conversion is that conversion from aldopentose to aldohexose. So which contain 5 carbon atom, and then it is that is the yes, increase ascent of the series. Also we can say that increase, there is a increase in a 1 carbon atom more, that is aldopentose to aldohexose. So 5 compound containing 5 carbon, and we are getting finally the compound containing 6 carbon atom. So here this is the important conversion, and this conversion is also known as Killiani synthesis, because Killiani is the name of scientist. So here it is as we know that aldose that is the aldopentose can be converted to the aldohexose, and a conversion of an aldose to higher aldose containing 1 more carbon atom, it is also known as ascent, increase, ascent of series. In 1886, Killiani is the name of scientist, suggested this method for ascent of series, and hence it is known as Killiani synthesis. So Killiani synthesis for the conversion of aldopentose to aldohexose consists of total 4 steps are there. So in the first step, aldopentose is first dissolved in dilute hydrocyanic acid to obtain cyanohydrin containing 6 carbon atom. In the second step, cyanohydrin is then converted to the aldonic acid by hydrolysis by aqueous barium hydroxide and then acidified by dilute sulfuric acid. In the third step, acid solution is filtered and evaporated to dryness to obtain gamma lactone. And after that, in the last step, number 4, gamma lactone is then gives a aldohexose on reduction by sodium amalgam in acidic media. So this is the step by step, it is shown in a 4 step, and we get converted from aldopentose to aldohexose. So this Killiani reaction can be used for the synthesis of aldose containing 4 to 10 carbon atoms. So here are shown in the slide the 4 steps. So in the first step, so here this HCN is added here, so CN is here added and CH here, CH, OH and CN is added, and after that we get this cyanohydrin compound. So HCN is get added, CN is here and EH is here. So and we obtain this compound cyanohydrin. Then it react with the P hydroxide and in presence of sulfuric acid. So this is oxidation, and this is converted into COH group, which is known as aldonic acid group. And then when aldonic acid is heated, we obtain this type of compound, 4 carbon, and this group get attached, and we get gamma lactone in previous stage. And after that, reduction with sodium amalgam in presence of acid, this group is converted into aldehyde group, and we get aldohexose, or also known as it may be a glucose or mannose sometimes. So this is the conversion. This is given by cyanohydrin. This is given by the scientist Killiani. Therefore, it is known as Killiani synthesis. So this is the ascent. So starting from 5 carbon, and we are getting compound with a 6 carbon atom. And after this, now another important conversion is there. That is Wohl's method, and conversion from aldohexose to the then aldopentose. So this 6 carbon. So there is the descent of the series. So this is the conversion aldohexose to aldopentose, so 1 carbon less, and aldohexose can be converted to aldopentose by the methods applicable, and which is known as descent of series. In this method, the product is aldose with 1 carbon atom less, and this method is given by and actually there are 2 methods to convert to the this conversion. One is a Wohl's method and second is a Ruff method. So in Wohl's method, this Wohl suggested a method and consists of the different steps. So in first step, aldohexose is converted to oxime by treatment with hydroxylamine, and in a second step, oxime is then treated with the acidic anhydride, which act as a acetylating agent as well as the dehydrating agent. And in a last third step, acetyl derivative is then treated with ammonical silver nitrate solution, and it remove acetyl group by hydrolysis and eliminate HCN molecule, forming aldopentose. So see, this conversion is better if the sodium methylate is used instead of ammonical silver nitrate. So this is the method given by Wohl, and is the name of scientist. So here is this NH2OH hydroxylamine is here added, and here we get this type of compound CH11NOH, and after that reaction with acetic anhydride, acetyl group is attached, so we have to take the 5 here, so 3, 4, 5, so one hydrogen from this and from this and from this get replaced, and in place of that we get acetic acids are formed, and acetyl group attached here 1, 2, 3, 4, 5, and we get this acetylated compound, and after that here we get this type of removal of this acetyl group, and we get this type of compound, and then again by remove this HCN, and we get this aldopentose. So hydrogen from this and HCN get removed, and we get the aldopentose. So starting from aldohexose, and we get aldopentose. So this is the method given by Wohl method, and 3 steps are there. And this conversion is also given by Ruff, is the name of scientist, and here aldohexose again converting to aldopentose, and in this Ruff method, this is the name of scientist Ruff suggested the method, and which include the 2 steps are there. In first step, aldohexose is first oxidized to aldonic acid by oxidation with mild oxidizing agent like bromine water, and in second step, aldonic acid is then neutralized by calcium carbonate and treated with H2O2 and FeSO4, which is known as Pentone's reagent, and obtain the aldopentose. So here this conversion is shown in 2 steps, and so here first oxidation, so aldehyde group converted into carboxylic acid group, so we get aldonic acid, and which is then react with calcium carbonate and H2O2 Pentone's reagent, and then COH group again converted into CHO group, and we get aldopentose, 1 carbon atom less, and there is a removal of other compounds. So these are the 2 important conversions given by Wohl and Ruff's, and after this we are going to see some important structures of some compound, and these compounds are 5-6 compounds are there. So first compound is a maltose. As we know, the molecular formula of maltose is a C12H22O11, and in case of this, as we know, this compound maltose also shows some reducing nature, and there is also some nature of monosaccharide units can also be explained. It also undergo oxidation, and we get maltobionic acid, and here the structure only we have to see. Structure is shown in the slide, and maltose is hydrolyzed by the enzyme maltase that is present in the yeast, which is specific for the hydrolysis of alpha glucosidic linkage. Therefore alpha, that is the carbon 1 of the non-reducing glucose unit, is converted to the carbon 4 of the reducing glucose unit. Therefore maltose has given the structure as shown by the 2 scientists, which is known as Fischer projection formula and Howard projection formula is shown here. So this is the structure for suggested by Fischer, and this is the Howard projection formula. So the structure is like this of this maltose. So only we have to see here the structure. So this is the first structure for the maltose, having the molecular formula. Second structure is also there, that is the sucrose, and sucrose also have the molecular formula C12H22 and O11. So in this case formula is same, but the arrangements are different, and in the slide also shown Fischer projection formula and Howard projection formula. So here molecular formula of the sucrose is similar to the maltose, and they also show non-reducing nature. In that case there are 2 units, glucose unit and fructose unit are shown in the slide, and they show non-reducing nature. Nature of the monosaccharide units, sucrose consists of when it reacts with the hydrolysis, then they give 2 product, glucose and fructose, having the similar formula, and this suggests that sucrose is made up of 1 glucose and 1 fructose unit, and there is a size of the ring of monosaccharide units, and nature of linkage in this compound are can be explained, that is the sucrose is a non-reducing sugar, and therefore both glucose and fructose unit in the sucrose are linked through their respective reducing, or we can say glycosidic center. Stereochemical nature of glycosidic linkage is shown in this slide, and the enzyme maltase, which is specific for the hydrolysis of alpha glucopyranosides, also hydrolyze sucrose. Therefore glucose is present in the alpha form, and fructose is present in the beta form. So this shows this fact suggests that the structure of this sucrose is shown in the slide. This is the structure for the sucrose. So this is glucose unit, this is fructose unit, and so this is in alpha form and this is in a beta form. So this is Fischer projection formula shown for the sucrose, and second is a Haworth projection formula shown. Two units again shown there, glucose and fructose unit. And third important compound is a structure of lactose. Again the formula of lactose is a C12H22O11, and this lactose also have the similar formula like that of maltose, and this compound also shows some when this lactose undergo the hydrolysis forming two monosaccharides, and these are the one is a glucose and second is a galactose. Both are having the same formula. Like maltose, lactose also reducing sugar and hence reduces tolerance reagent and failing solutions, and also it react with the hydroxylamine and to form oxygen. It also undergo oxidation and forming is also oxidized and forming lactobionic acid. So structure formula of this compound is formula is same, and it also show reducing nature. Monosaccharide units are also there, and here nature of glucosidic linkage is present in this compound. And again now there are glucose unit and galactose unit. One is a reducing and another is a non-reducing unit shown, and here this is the compound. Lactose is hydrolyzed by the enzyme lactase, and shown in that slide, which is specific for the hydrolysis of beta glycosidic linkage, and here lactose is a galactose, but here the structure is shown, and alpha and beta forms of lactose differ in their configuration at anomeric carbon marked by the asterisk shown in that slide. So this is the structure for the Fischer projection formula shown and Haworth projection formula, both for the this lactose. And next important compound is a starch, and starch is having formula C6H10O5 n times, and it is one of the most important source for the carbohydrate. And here we have to see the structure, and structure it is very important compound, and this compound starch have the molecular formula shown, and here in this formula n varies from 200 to 300. N may be minimum 200 to 300 are there, and nature of monosaccharides units they contain. When they this compound undergo hydrolysis, they yield maltose, glucose, different types of compounds, monosaccharides they formed, and monosaccharide units are formed. And nature of linkage, when amylose upon partial hydrolysis with enzyme diastase, they form maltose, and we have this structure shown in this slide, and linkage are there. And we have seen that in maltose the two glucose units are joined together by alpha glucosidic linkage, and it is logical to say that large number of glucose units joined together by a alpha glucosidic linkage C1 at involving C1 carbon 1 and carbon 4, and structure of this compound is shown in the. So this structure of starch is supported by some fact that complete methylation of this starch produces maximum dye substitution product. So X-ray analysis also shows some support for the structural analysis, and look like an helix structure or in a complex structure like that. So this is the structure for this starch, look like helix. So another is a cellulose, and cellulose also have similar type of structure. Formula of this starch, cellulose is a formula C6H10O5, and this cellulose is very important compound, and they have the molecular formula 6,6H10O5 and nature of monosaccharides are there also. It contains number of glucose unit when it undergo hydrolysis. Large number of glucose units they formed, and nature of linkage is also there. That is shown in the here. Cellulose is made up of cellulose unit, and cellulose is similar to that of maltose, except that is hydrolyzed by the enzyme emulsion. So the structure of the cellulose is shown in the slide. Segment of cellulose molecules which is repeated here shown. This is the segment, this is continuous, and a long chain is formed of the cellulose. So this is the structure for cellulose, and next is the structure of ribose and deoxyribose. So molecular formula of this compound is a C5H10O5, and this is ribose and this is deoxyribose. So arrangement slight change is there of hydrogen and hydroxyl group. So A is ribose and B is a deoxyribose. Structure we have to see here only. So today we have seen the different conversion from glucose to fructose and fructose to glucose. Also we have seen some Kiliani synthesis, that is from conversion of Aldopentose to Aldohexose, and by two methods, so Wohl and Ruff, the conversion from Aldohexose to Aldopentose. So and after that some important compounds are there which the structure of that compound already we have seen.